Comet 3I/Atlas has emerged as one of the most extraordinary astronomical discoveries of recent years, compelling scientists and skywatchers alike to rethink many long-held assumptions about the behavior and origins of interstellar objects. As it travels through our solar system on a path unlike anything previously recorded, this mysterious visitor has already begun to reshape our understanding of orbital mechanics. Its exceptionally high eccentricity, exceeding 2.5, is not only unprecedented, but also fundamentally challenges the models astronomers have used for decades to classify and predict the motions of comets. This single measurement alone reveals that 3I/Atlas is more than just another icy wanderer. It is an interstellar traveler with a story that began far beyond the boundaries of our sun's influence. The comet's extreme motion through space provides crucial insight into the chaotic, unpredictable dynamics of the galaxy, raising new questions about the formation and evolution of planetary systems scattered across the Milky Way. Astronomers first realized something unusual was occurring when they began tracking the object's trajectory. Unlike typical solar system comets, which follow elongated elliptical orbits that bring them back toward the sun time and time again, 3I/Atlas was moving too fast and following too sharp a curve to be bound by the sun's gravity. The key to deciphering its behavior lies in its eccentricity, the number used by physicists to quantify how stretched or elongated an orbit is. Orbits with an eccentricity of 0 are perfect circles. Those approaching 1 become more elongated. And once the value exceeds 1, the object is no longer gravitationally tethered to the sun. Instead, it follows a hyperbolic path, meaning it arrived from interstellar space and will eventually leave our solar system forever. With an eccentricity surpassing 2.5, 3I/Atlas has moved well beyond even the most extreme ranges known to scientists. This makes it not just interstellar, but one of the fastest and most unusual interstellar bodies ever detected. This discovery offers a rare chance to observe an object untouched by the conditions that shaped our solar system. Most comets originate in the Kuiper Belt or the Oort cloud, where they spend millions of years as frozen relics before occasionally being nudged into the inner solar system. Their compositions, orbits, and behaviors, therefore, reflect the early history of our sun's formation. But an interstellar object like 3I/Atlas formed around a completely different star, under conditions that may have been dramatically unlike those of our own neighborhood. By studying it, researchers hope to glimpse clues about distant planetary systems, how they formed, how their materials coalesced, and what kinds of cosmic processes operate far beyond our observational reach. The comet's speed and trajectory suggest it may have been ejected from its home system during a period of gravitational instability, possibly involving the migration of giant planets or the close passage of another star. In young planetary systems, such violent interactions are common, often sending debris hurtling into deep space. Over millions or billions of years, these objects drift silently between the stars, carrying with them chemical compositions and physical structures that may differ significantly from anything found in our own system. When one of them happens to pass close enough for us to observe, it becomes a valuable scientific time capsule. With 3I/Atlas, astronomers now have that opportunity, a glimpse of material forged under alien conditions, shaped by forces we have only begun to understand. The fact that 3I/Atlas challenges established models is not surprising when considering how rare interstellar observations have been until recently. Only a handful of such objects have ever been confirmed. The first, 1I/Oumuamua, puzzled scientists in 2017 with its elongated shape and unexpected acceleration. The second, Comet 2I/Borisov, was more conventional in appearance, but still offered invaluable insight into the composition of foreign cometary material. Now, with 3I/Atlas breaking records with its extreme eccentricity, astronomers are beginning to realize that interstellar objects may be far more diverse and unpredictable than originally believed. Each new discovery expands our understanding and forces scientists to update models that were developed largely from studying solar system objects alone. The comet's unbound path illustrates the limitations of gravitational influence. Our sun, massive as it is, cannot capture or retain a body moving at such incredible velocity. This is why the eccentricity number is so important. When scientists saw that 3I/Atlas exceeded the limit of 1, they understood immediately that it must be a visitor, not a resident, but exceeding even the typical hyperbolic values seen in rare gravitationally perturbed comets, and instead reaching over 2.5 signifies a journey that began unimaginably far from our system. To generate such a trajectory, the comet likely experienced powerful interactions, perhaps a close encounter with a giant planet larger than Jupiter, or a slingshot effect around its original star. These scenarios imply the existence of dynamic, perhaps turbulent systems elsewhere in the galaxy. From Earth's perspective, the comet's passage offers a fleeting spectacle. Though too faint to be easily visible without telescopes, its presence inspires a sense of cosmic scale and interconnectedness. For centuries, humanity has watched comets appear suddenly in the night sky, interpreting them through myth, superstition, or science, depending on the era. But never before have we been able to trace a solitary comet's path across the galaxy, following it not just through our own skies, but through the larger structure of the Milky Way. Each interstellar visitor reminds us that our solar system is not isolated. It is part of an enormous, dynamic environment where stars, planets, and comets interact over staggering distances and time frames. One of the most intriguing aspects of studying interstellar comets is the potential they hold for revealing universal building blocks. Many theories propose that the basic materials of life, such as organic molecules, are common throughout the galaxy and capable of being transported by comets. If 3I/Atlas contains unusual compounds or structural features not present in solar system comets, it could provide clues about conditions in its home system. Conversely, if its composition is similar to comets formed around our sun, that would suggest a surprising chemical consistency across different stars. Either finding would have profound implications for theories about how life might emerge elsewhere in the universe. While 3I/Atlas travels on its one-way journey back into interstellar space, astronomers are racing to gather as much data as possible. High-powered telescopes are being used to measure its brightness, analyze its coma and tail, and determine whether it behaves more like typical comets or displays unexpected characteristics. Understanding the rate at which it sheds material, the composition of its dust, and the structure of its nucleus could provide critical information that shapes future models of interstellar comet behavior. Each observation helps refine our understanding of how such objects respond to solar radiation, gravitational forces, and thermal stress, factors that affect all bodies entering the solar system, but which may affect interstellar comets differently due to their unfamiliar origins. Even beyond scientific investigation, the story of 3I/Atlas captures the imagination. It is a reminder of how vast the universe truly is, how many mysteries remain unsolved, and how each discovery has the power to overturn assumptions we once regarded as settled. For many people, the idea that a comet could travel from a distant star system, pass briefly through our own, and then disappear forever into the endless dark is both humbling and awe-inspiring. It reinforces the notion that the cosmos is full of wanderers, objects drifting between suns, carrying secrets from places we may never visit. And every time one of these wanderers enters our field of observation, even for a brief moment, it offers a precious chance to learn something new about the galaxy we all share. In the end, 3I/Atlas stands not just as a scientific anomaly, but as a symbol of the unpredictable and ever-changing nature of space. Its unprecedented eccentricity challenges the foundations of orbital physics. Its behavior forces scientists to refine their models. Its origin sparks curiosity about worlds beyond our own. And its fleeting presence reminds us how small our place is within the grand architecture of the universe. As it continues its silent voyage out of the solar system and back into the interstellar void, it leaves behind a legacy of discovery, wonder, and the promise that many more cosmic travelers may follow, each with its own extraordinary story to tell.